Okay, here we are. We are ready to tackle neural networks, so give this a nice title. And hopefully you've watched the video that I sent the link to in the email, the 3 blue, 1 brown video on neural networks. It really helps set the stage on what they are, how they work in much better graphical format than I could ever hope to do drawing on a board. So high production value there. So let's start off with a very simple neural network, and we're going to have x of 1, x of 2, and x of 3. Okay, and they are going to be connected to and feeding into this node over here, which will output our hypothesis. Okay, now this hypothesis is going to be calculated again by feeding our h of x is equal to our theta transpose x into the sigmoid function, into the sigmoid. So it's going to look like what we've seen before. H of x is equal to 1 over 1 plus e to the negative theta transpose x. Okay? And in addition, where are the thetas? Well, we have our x's up here. We don't have our thetas listed. But our thetas are going to be the, I guess, wires or lines that connect each of the nodes. So we've got our, in this case, theta 1, theta 2, and theta 3 for the weights that are going to connect each of the nodes to the subsequent nodes. Okay, and again, our thetas are the weights, the parameters, and our x's are our inputs. Okay, now I haven't drawn on here something that is missing, and that is x of 0. I will put that in the drawing from here on. I will try to remember to put it in for the drawing from here on, because our x of 0 is equal always to 1, but we will have x of 0 connected to each of the subsequent nodes, and we're going to have a theta 0 weight. And so we've talked about theta 0 before. Theta 0 is our bias or our offset. I think we've called it baseline. And when we talk about the theta 0 in terms of neural network, I'm going to be referring to it pretty much consistently as either the bias or the threshold for our system. And so this is our bias / threshold. If I can write threshold, I think that's how you spell it. So this is our very simple model where we have our input nodes are feeding into a node that then outputs our hypothesis function by feeding theta transpose x into the sigmoid function. Alrighty? Okay, so we are going to expand the model a little bit. We'll start with our x of 1, x of 2, and x of 3. And don't want to forget our x of 0, which is always equal to 1. And we're going to now feed the inputs into new nodes. So these new nodes are going to have a label of A, and this is the first node, so it's a sub 1. And I should mention that the initial layer is layer 1, and this is layer 2. Okay, so these vertical columns are our layers of our neural network. So this is the first node labeled A in layer 2, and this is A sub to the second node in layer 2, and this is A sub 3 in layer 2. Okay? Now, why am I calling these A's? Well, first off, let me draw all of my connections between these. So I've got all the different arrows coming from layer 1 into layer 2. Yep, that's a lot of arrows you get to draw when you start doing neural networks. And so we have layer 1 fully connected to layer 2. And the reason that I'm calling this A, I'm labeling each of the nodes in layer 2 A, is because these are activations. Okay, and the activation is what you get, it's the value that you get once you feed in, let's do theta transpose x into the sigmoid function, and that is going to give me my activation, or I'm going to call it the G function, the sigmoid. Okay, so the sigmoid, I feed in theta transpose x, and I get an activation out. Now, to clarify some of this notation, we're going to say that A sub 1 superscript j, that is going to be the activation of node 1 in layer j. Okay? And then we're also going to have a new notation for our weights, our parameters. We're going to have theta. Here we go. Notice the order that I'm reading this. 0 to 1, and then j. This is the weight, the parameter that maps from node 0, this one, to node 1. Note that strange order, to node 1, starting in layer j. Okay? So the node where these zeros and ones comes from which one of the nodes they are vertically in the list. So the starting node to the finishing node, and the layer that the starting node was in is the J. So let's pick one of these. Oh, let's see. I'm going to pick this one right here. Let me draw a little arrow to it. Otherwise, I don't think we'll be able. So this connection is between node 1 to node 3, and it's starting in layer 1. So this one would be theta, and it's going to go from node 1 to node 3. So 1 to 3, and the starting layer is layer 1, so superscript 1. And that will let me keep track of what all the weights, where they are, what two nodes they're connecting as we go along. And just remember that the starting node is the farthest right number, and the ending node is the left number. So we write it backwards, and then the layer that it starts in is up top. And so with that notation, we can actually, I'm going to attempt to draw a much more complicated set of neural networks. So here we go. Wish me luck. Okay, so we're going to have x0, x1, x2, and x sub 3. Alrighty, and then this is going to feed into, we've got A1 layer 2, activation 2 in layer 2, and finally activation 3 in layer 2. I can write 2 there. There we go. Okay, now we're going to connect all of the input nodes into our layer 2 activations. So to do that, I'm going to attempt to use different colors. Hopefully it'll show up nicely. Let's start with, let's see, we'll go for the first activation. So we're going to have arrows coming in from each of the nodes, the input nodes, into that activation. Okay, and I'm going to label all of the weights. And you know what? Let me draw the lines first, and then I'll do all the weights. So that way I don't have to go over my weights. So let's see. Let's change colors now. Oh, let's see. Purple sounds good. So for the second one, we're going to have all the input nodes pointing to the second activation. And then finally, let's go red. For the final one, we'll have all of the inputs pointing to the last activation. Okay, so now let's fill in all of the weights. So go back to green and fill in these. So this one is going to be theta, and I'm going from node 0 to node 1. So 0 to 1. And then the layer that I'm starting in is layer 1. So that's a 1. Okay. Then this one is going to be theta node 1 to node 1. So 1 to 1 in layer 1. This one is going to be theta 2 to 1. So 2 to 1. And then that's in layer 1. And finally, this one, which is going to be from node 3 to node 1. So 3, 1, and layer 1 is where we started. Okay, so we have all of those weights. Now we'll try the second activation, all of the weights that lead to that. So we'll go back to purple and label these weights. So this first one is going to be going from node 0 to node 2. So 0 to 2, and it starts in layer 1. Then I've got for this one, it's going from, oh, that's the same one. Hold on, let me erase that. Oh, that's funny. Alrighty, so erase that one. Picked the wrong one. Okay, so let me go back. And this one is the one I wanted to do the weight for. So this one, we're going from node 1 to node 2. So 1 to 2, layer 1, where it starts. This one right here, this weight, it's going to be a little bit difficult to fit in, but I'm going from 2 to 2. So 2 to 2 in layer 1. And finally, this one right here, I'm going to be going from node 3 to node 2. So 3 to 2 and in layer 1. Alrighty. Now, let's wrap it up with the last activation. So we're going to have this weight right here, the very first one. Well, that's going from node 0 to node 3. So 0 to 3, starting in layer 1. Then this weight is going to be from node 1 to 3. So 1 to 3, starting in layer 1. This one right here is going to be from 2 to 3, 1, and finally this one is going to be from 3 to 3, layer 1. Alrighty, now let's write out what all of the activations, how we actually calculate them using this kind of a blueprint. I realize it's a little bit messy, but I hope you can follow along with it. So let's go back to our normal color and fill in what we've got. So we're talking about activation 1 in layer 2 is going to be given by, well, the sigmoid function applied to, we've got our theta times this node, so we're going to have theta 0, 1, 1 times x sub 0 plus the next weight, so theta 1, 1, layer 1 times x sub 1 plus next one, theta 2, 1, layer 1, x sub 2 plus theta 3, 1, layer 1, x sub 3. And that will give us the first activation value. You take this summation, this theta transpose x, send it through the sigmoid function, and that gives you the activation. All right, let's follow suit with the next one. So we've got a sub 2 in layer 2. That activation is going to be the sigmoid applied to, well, we've got our, this is now the purple, so I've got this weight, theta 0, 2 times x naught, so theta 0, 2, layer 1 times x naught, plus theta, now for the next weight from this node to this node, so 1, 2, and layer 1, x sub 1, plus, and then we'll have theta, this one right here, theta 2, 2, layer 1 times x sub 2, plus, finally, theta 3, 2, layer 1 times x sub 3. Okay? And finally, a sub 3, 2 is going to be sigmoid applied to. We've got the very first one, that weight is 0, 3, so theta 0, 3 times x naught plus theta 1, 3 times x sub 1 plus theta 2, 3 times x sub 2 plus theta 3, 3 x sub 3. Alrighty, there you have how you calculate all of the activations using the individual weights and inputs. And the very next step is we're going to extend this just a little bit to make it slightly more robust. So I will see you in just a second. Okay, so we are going to erase all of this, and let's see if I can make my eraser size larger. There we go. I want to extend this network to something that more resembles what you'll actually see inside of a neural network. That looks pretty good. Alrighty, so let's now go back and draw some new nodes. We are going to have a layer 2 feeding into layer 3. So I'm going to draw a node right here. And that node I'm going to call, there's only going to be one of them, so it's going to be activation 1, but it is in layer 3. Okay? And I'm going to have all of layer 2 nodes feeding into layer 3, but that means I also need to have an A naught from layer 2, which is, as always, equal to 1. So here we go. Let's now feed forward, and let's try blue. So I'm going to have all of these nodes feeding into the new activation. Okay, so I'm now going to label all of the weights. So this weight is going to be feeding from node 0 to node 1, and it starts at layer 2, so 0 to 1, layer 2. This weight is going to be node 1 to 1, layer 2. This one is going from 2 to 1, layer 2. And finally, we're going to have node 3 to 1, 3 to 1, layer 2. So that gives us all of our weights. And we're going to say that this will output to our hypothesis. Okay? So now that we have this represented, we're going to write down what leads to this activation, kind of like what we did before. So we're going to have, if I can find a good spot for it, A1 third layer is equal to the sigmoid times, well, we're going to have the first weight times the previous nodes. This is going to be theta 0 to 1 layer 2 times A naught from layer 2 plus theta 1 1 layer 2 times A1 layer 2 plus, we'll have theta 2 1 layer 2 times the previous activation, so that node is A2 layer 2, and finally theta 3 1 layer 2, and then that's times the previous activation, A3 layer 2. Alrighty, so that is how we get our final activation. And notice that each of the nodes as we go through is calculated on the previous layer's nodes. So the pattern extends no matter how many layers we have. You're going to do exactly the same thing. So when you are feeding forward in our neural network, you actually only have to consider one layer at a time. The previous layer is what sets all the values for the current layer. And I want to make one last addition to this, because notice that we've had over here for our input layer, we've had x0, x1, x2, x3. We can represent that instead as just activation of layer 1. So all of these would be, this would be A3 layer 1, A2 layer 1, etc. And if we did that, it would be consistent with all of the other layers and allow us to kind of reuse the same code without having to change any of our variables. So if I think of the inputs as just the first layer activations, if you will, I can also think of all of these biases that we're putting in. When I say bias, I mean the very first theta here times our very first node, and likewise for this one. I can now represent the bias as something that looks like, oh, let's see, that would be, let's go with theta 0 to I of j. This would be the bias for node I in layer J. If I can write that in there. So in this case, if I have, since the bias is always going to be the very first node, the 0th node, this is always going to be a 0, and then it will point to, if I'm looking at the bias that leads into this value, it's going to be the theta that starts at 0 and leads to this node, so node 1, and actually I guess that would be layer J plus 1 if I count it that way. But you get the idea. When I'm talking about the biases, I'm talking about these values, and then if I can, I need to change color. Let's see, I'll change to, let's go with orange. Then I'm also talking about this one right here. Those are the biases, and notice that each of the biases does not get anything fed into it from the previous layer because its value is always 1. What changes and what lets you set the thresholds is the weight here, these parameters. So that's what we're going to be working with in the next video, where we are actually going to use simple neural networks to model Boolean logic gates, or Boolean logic functions in the case of math. I've done enough computer science where I think of them as gates now. But we will tackle that next video, and I hope you have enjoyed the introduction, the very colorful introduction to neural networks. So I will see you very soon for the video on the logic gates.